In the electric vehicle simulator that we've just described, you note that we made a simplifying assumption that the battery pack voltage was constant overall the whole drive cycle, and we use that to simply convert a demanded battery pack power into a demanded battery pack current. Now we know this is not the case. We know that the voltage of a battery varies quite a bit depending on the usage of the battery, the past usage and the present usage. And so for a good simulation, we would want to be able to change this, to improve this. Now, there's a problem, though. It's one that we're going to overcome in this section, so it's not a significant problem, but there is a problem, and that is that the simulation that we just looked at had a demanded battery pack power. And all of the models that we've created, the input to the model is not power, but instead the input is equal to current. So we need a way to convert a demanded battery cell power. Let's look at the cell level first, not the pack level. Let's convert a battery cell demanded power into a battery cell demanded current, because once I know the current, I can simulate using the model equations that we have now. So that's the first objective of this topic. Then we have one other objective also, which is suppose that the demand is a constant terminal voltage. In other words, we want to set the output and compute the current that actually does that. So we'll look at those in this section. First is constant power simulation, or to determine what the current is to get a certain output battery power. And we look at the enhanced self-correcting cell model, and remembering the structure of the model, it said the present state of the battery cell was some A matrix which depended on the input, so it changes with time, times the present state plus some B matrix times the input current, something like that. And then the cell voltage was equal to open circuit voltage plus hysteresis, and then minus a diffusion voltage, and then minus I times R0. There's something that's super important to grasp from this, is that all of these elements in voltage are a function of the state members at this point in time. Open circuit voltage is a function of state of charge, which is one element in X. Hysteresis is the M maximum hysteresis constant multiplied by the hysteresis state, and the hysteresis state is in the state vector X. And then the diffusion voltage is the sum of the diffusion currents multiplied by respective resistances, and the diffusion currents are members of the state vector X. So all of those are functions of X. And furthermore, X is not a function of the present current, the instantaneous current right now. It's a function of the previous current. So when I am looking at the present battery cell voltage, it comprises one part, in fact most of it, is not a function of the present current. That part has already been determined by the previous values of current. The only thing that has any influence whatsoever on the present value of current is this minus IR0, plus of course this factor here, but I can't change that with the present value of current. So I think that's what I tried to say in words here. The present state does not depend on the present current. Instead, it depends on previous values of current. So cell voltage has a fixed part. We'll call this the fixed part. And that part does not depend on the present value of cell current. And it has a variable part. So this here is the variable part. And that part does depend on present cell current. So if we, in our nomenclature, give this notation to the fixed part, and call that VFK, then we have VK equals VFK minus R0 times IK. Now that's really helpful. We're going to see how helpful that is in just a minute, but without that, it would be very difficult for us to compute a value of current that gives us a constant power or a constant voltage, because we would have to solve, basically, we have to solve this equation for I in order to get a desired voltage. And if the fixed part wasn't fixed, that would be more challenging. Let's proceed and look at that. The battery cell power, P sub k, is equal to, by definition, just the voltage at the terminals multiplied by the current, so Vk times Ik. And we have just said, well, Vk is equal to Vfk minus R0 times Ik. So I make that substitution, and of course we're still multiplying by Ik. I would like to solve this equation for the value of Ik that gives me P, the desired cell power. To do that, I rearrange the equation, and by bringing all of this stuff over to one side of the equation and rearranging, so I get R0I squared minus VFI plus P equals 0. Okay. I have a quadratic equation. Quadratic equation is something, a quadratic equation in I, and I can solve it. And I can get a value of current then for any desired power. So this is what we do. Every time sample, we solve this equation. I compute the fixed value of voltage for this time sample based on the present state, and then I also say that I is that fixed part, Vf, from here, plus minus the Vf squared, and then minus 4 times R0P, all divided by 2R0. Standard quadratic equation. There are two solutions, and we have to decide which solution we want. And we can prove, I don't do that here, we can prove that one of the solutions is obtained by forcing a negative cell voltage and one by a positive cell voltage. For example, P equals IV. I could say a power of 10 is equal to 2 times 5. That's a pretty high voltage, but I just made that up. Or it's equal to minus 2 times minus 5. So one of these solutions actually makes the cell voltage negative, and that's not a possible solution for us. So we determine to take the current, which is the least positive. Remember, a positive current is a discharge current, so a very big positive current is going to tend to drive a cell voltage more negative. So we take the least positive by using the minus here instead of the plus here, and that gives us this equation here. So in order to simulate a power, a desired power over a specific interval of time, this is how we do it. We solve for current using this quadratic equation, and we get the right input current. Now sometimes we also would like to be able to simulate a constant voltage. In other words, we have to solve for the battery pack current that will result in a desired terminal voltage. So we want to solve for the I that causes V to be equal to Vf minus IR, and V is given. So we simply rearrange and say I equals Vfk, the fixed part, minus the desired voltage, Vk, divided by R0. This example shows both of these in operation, and one time we might want to use them is in charging a battery cell. When I'm charging a battery cell, often what I will do is I will use constant current, that's current, until the battery cell voltage hits a maximum voltage limit. And at that point, so the voltage is going up like this, and at that point, when I hit that limit, I hold the voltage constant instead of holding the current constant. And holding the voltage constant makes the current decay in something that looks very much like an exponential decay, although it is not exactly that. So this is called constant current, constant voltage charging, because I have first step is constant current, second step is constant voltage. Sometimes instead of doing constant current, we would do constant power first, which is a slightly different thing. So we would do constant power than constant voltage charging. Both of those are possible, both of those are done, and now we have the ability to simulate both of those, as we shall see in the code below. It's quite straightforward to do it now that we've gone through this little exercise. In a lab test, constant current, constant voltage is often used. In charging an actual battery pack, it's more common to do constant power charging than it is to do constant current charging. And so that first step would change. And what you do after you hit your voltage limit is something that depends on the OEM and their design principles. Sometimes they'll hold the battery pack voltage constant. Sometimes they'll just do another constant power cycle with smaller power. Just different things you can do there. Here we'll look at the constant power, constant voltage for a single cell only. They're quite straightforward to simulate now. What we're going to do is we're going to consider that we have a battery cell that's initially at a 50% state of charge, and we would like to charge that cell to a maximum given voltage using either a constant current, constant voltage, or a constant power, constant voltage profile, just to look at what happens. I have some code below. We'll look at that in a minute, but let's look at the results first. On the left, top left, we see plots of battery or cell state of charge versus time. We notice that we start at 50% and we end up at 100% state of charge. And the blue line, the solid line, is constant current. So you can see that the state of charge is increasing linearly as I do constant current because we're simply Coulomb counting. And then you'll notice this interesting behavior where after a point, and it's after around here, the state of charge stops going up linearly and then starts curving, approaching the 100% state of charge with a tapering rate. The constant power, constant voltage, the power level was scaled to be similar so that the rate of charge would be similar to the constant current. Of course, we could do a faster constant power, constant voltage sim than this, or a slower one. Just depends on the power level chosen at the beginning. But we chose, I believe it was a 35 watt for this cell power level, as we shall see. Then in this case, we start out very similar current levels, and so the state of charge is changing at a very similar rate. But as the state of charge increases, the cell voltage increases. And power equals current times voltage, and if this is going up, for this to be constant, then current must be going down. So I would not be charging quite as quickly if I start charging at exactly the same rate. The plot directly underneath shows cell current versus time for both of these cases. It's charging, so the current is negative. And the constant current, constant voltage starts with a charge current of 9 amperes. And it goes 9 amperes until roughly 1500 seconds, at which point I hit the voltage limit of the cell, the maximum voltage. And then it switches over to a constant voltage mode. And we see that I have a roughly exponential decay of cell current versus time when I hold that voltage constant. Now I don't have a plot of, I do have a plot of voltage versus time, I'm sorry, and that's over here. And we can see the blue line does in fact hit the voltage limit, roughly 1500 seconds, and voltage is held constant in that. And then we also see cell power versus time. In the constant current profile, power equals I times V. If this is constant and this is increasing, then power must be increasing too in an unsigned sense. So we can see that power starts out at roughly minus 35 watts and it increases to maybe minus 38 watts or something before it hits the voltage limit and then starts going down. The constant power, as we said, the power has to taper off in order to, the current has to taper off in order to make constant power. Over here we see we actually do achieve constant power, and we get to our voltage limit a little bit later because of that. And then we taper off the charging as well if the power is going to cause the voltage to exceed the limit. Both of these cells are charged to, say, 99% in roughly the same amount of time. So roughly, I would say 2,000 seconds in this example. Even though one of them is a little bit gentler, the constant power might be a little bit gentler charging profile in this case than the constant current was. So these pictures probably are worth looking at and thinking about for a little while. But they do show that we can do the simulation. Let's look at some code. It's not difficult code now that you've seen the math behind it. You can copy and paste this code directly into your MATLAB program, assuming that you have a cell model, an E1 cell model from last semester. If not, email me and I can point you at it. So I start by clearing the workspace and closing figures and clearing the command window just to clean things up before the program starts. I load the cell model of the ESC variety from a data file. I'm going to simulate for 3,000 seconds basically at 25 degrees Celsius, and here I am retrieving from the model structure all of the parameters required for the model to be able to simulate. So Q is capacity, RC is the resistor capacitor time constant, R is the resistor capacitor resistance, M is the hysteresis magnitude, G is the hysteresis rate constant, and R0 is the series resistance. I set the maximum cell voltage to be 4.15 volts, and now I simulate constant current, constant voltage. I pre-allocate some memory to speed up the simulation. So I'm going to store state of charge Z, voltage V, current I, power P for plotting. The initial state of charge I set to 50%. The resistor capacitor current I set to 0. Hysteresis state I set to -1. And the constant current I set to be 9 amperes when I'm in the constant current mode of this CC-CV charge. And then I iterate. First, I find the present fixed voltage, which is the open circuit voltage depending on the present state of charge rather, the hysteresis voltage depending on the present hysteresis, and then the diffusion voltage depending on the present resistor capacitor current. That's the fixed voltage. Then I compute the current that would be required to achieve the maximum voltage of 4.15 volts as V minus Vmax over R0. And if that current is smaller in magnitude than the constant current value of 9 amperes, then I'm going to use I'm going to use this computed current because using the constant current would exceed my voltage limits. But if my constant current does not exceed the voltage limits, then I will use that instead. So that's what this command here does. It's minimum in an unsigned sense, but maximum in a signed sense because charge current is negative. So that's how I compute the input current. It's either going to be the constant current or it's going to be the constant voltage current, depending on which results in the smaller cell voltage, basically. And then, based on that, I update the state of charge equation using Coulomb counting. I update the resistor capacitor currents. I update the hysteresis state. And then I store the state of charge, the terminal voltage, the current, and the power. And then I plot stuff. So that is the constant current, constant voltage part of the simulation. Now we go into the constant power, constant voltage part. I reinitialize some states So state of charge gets reinitialized to 50%, the resistor capacitor current to 0, hysteresis to -1, and the power to 35 watts, and that should say 35 there. The program loop is almost exactly the same. So first I calculate the fixed part of the voltage, exactly the same as before. Then I compute the current required to achieve constant power, and that solves that quadratic equation with the sign of the quadratic making voltage positive. And here we do the limits. So I say if the constant power would result in an overvoltage, then instead I do the constant voltage instead. And so that helps me determine which power I'm going to choose. Which current I'm going to choose. It's either this one or it's this one. Same idea as before, but implemented slightly differently. And then the rest of the code is exactly the same. We update state of charge with Coulomb counting, update diffusion current, update hysteresis voltage, store things just as before, and now I am going to plot over top of the other plots the state of charge, the voltage, the cell current, and the cell power. And that's it. So using these ideas and this code, the models that we developed, the circuit model we developed last semester, all of a sudden becomes a lot more valuable. Instead of just doing a constant current type of simulation, or a simulation where the current is the input, I can now have power be the input, or I can have voltage be the input and the output, and I can simulate a whole variety of things. One more topic in this set of notes has to do with being able to simulate battery packs. So not a single cell only, but now multiple cells wired in parallel and in series, and there's some things that we can learn from that. So let's look at that, and then we'll move on to other topics.